All right, fingers crossed. I hope the audio is working. Okay, so yeah, this is what we were talking about last time. When you're doing the chain rule, there's something fundamentally undesirable about writing things like this. I'm going to be composing these functions. What comes out of f needs to be what goes in to g. That's not how this is set up, right? So just so much easier to, don't do any of this. That's just pointlessly confusing. Make decisions on what you're going to call the various variables at these sort of three stages of the composition. There's the original input, there's the intermediate variable, and then there's the eventual output. Give them all different names, obviously. They're different variables. Of course we would give them different names. And having done that, we see it's okay to write f in terms of x, but we really ought to rewrite g in terms of a different dummy variable, y. Seems like a reasonable choice here, like so. And then you do that when you're looking at the derivative of the composition, partial of that with respect to that. Then be as careless as you like, in some sense. You don't have to worry about, do I have to remember what am I going to plug into what, right? It does that for you, right? And so life just becomes a lot easier. Okay, so that was an example, hopefully a very relatable example, the purpose of which is to show you exactly what the same problem is in multivariable. Same exact situation. So if you're going to compose a couple of functions, and here's a couple of multivariable functions, and there's quite a bit going on here with the definition of these functions, and so much written on the page, you might not notice that, again, these are written kind of unnaturally as they're coming to you here, because they're both written in terms of the same dummy variables. And we're going to compose them. Look, see, it says right here, composition, G compose F. So if you're going to compose them, then as sort of suggested here, it may be okay to leave your f in terms of x and y, but you really ought to rewrite g in terms of u and v. So we're going to not do that and instead do that. Same function. I didn't change g at all. I'm just writing it in terms of different dummy variables. Everybody happy? All right, and at this point now life is good, and it's just a matter of writing down the chain rule. No big deal. The chain rule says you look at the derivative matrices of the two functions, and the derivative of the composition is the product of the individual derivatives. Right? Matrix form of the chain rule, very natural. And then now do make a point of keeping them in the right order. Right? The function that acts first is on the right in the algebra. It's on the right in the composition, it's on the right in the chain rule, but it's on the left in the diagram. And the function that acts second in the composition, well, its derivative is second, which is on the left in the algebra, but it's on the right in the diagram. And I make a big deal out of this because I got stung really bad on this one time, and I've never forgotten it. And so I just want y'all to be able to learn the lesson without having to get stung like I did. Okay. All right. And notice I'm not even paying attention as to where I compute this. I just took the DG matrix and just kind of recopied it right there. And I took the DF matrix and I'm just kind of putting that over here. No big deal. And then, yeah, eventually I need to rewrite everything in terms of x and y. After all, the composition is a function of x and y. The derivative should also be in terms of x and y. So I got to rewrite all of this stuff here in terms of x and y. And how am I going to do that? I need to get all this on the same page. That's good enough. How am I going to get, for example, this u right there? How am I going to figure out what u is in terms of x and y? Well, u, being as it is the first input to the g function, is also the first output from the f function. And so it's x squared plus y squared. So that u, just plug in x squared plus y squared. And again, the notation is doing your work for you, right? It's doing your bookkeeping for you. If you have a clearly indicated diagram showing what variables are doing what roles with respect to which functions, you just read straight off there, u is x squared plus y squared. And then likewise, what am I going to do about this v right there? Well, okay, v is, it's the second input to g, which means it's the second output from f, which means it's x squared minus y squared, like so. Yeah.
I feel like I'm getting lost. I know how to go like the derivative matrix of f, but
Yep.
then for g, like I think it's
Yeah, it's just partial derivatives. Yeah.
no, like from the f of, because if you take the chain rule, it's like g, like the derivative of g with like f of x inside.
Well, with the business about plugging in the f of x, that's kind of what this change of, having rewritten the dummy variables,
Okay.
it kind of automatically does that for us. Effectively, that's what we're doing here.
Okay.
The beautiful thing is, because I've made a reasonable choice of my variables, dg is just, it's just a matrix of partials. Just compute the various partials.
Oh, okay.
Yeah, and that's what's nice about this point of view, is that I get to just be kind of careless about where I'm evaluating, and my variable choices will do the plugging in for me.
Okay.
Yeah. All right. Okay, now this is a special case of a larger problem. When you set up a chain rule problem, you got to make sure that you follow all of the rules. And fundamentally underneath all of this is that when you draw yourself a diagram, it has to represent a composition of functions. Now, just to be clear, why? Because that's where our chain rule came from, right? If you go back to where we first wrote down, too far. Here was our first multivariable chain rule. We wrote down that derivative matrices multiply by making an argument that was literally about one function followed by another function and thinking about their composition. So our chain rule, the only chain rule that we know, comes from literally looking at a composition, that's a strictly defined term, composition of multivariable functions. Now, we rewrote it a little bit eventually. We kind of reconceived of it. We have this kind of point of view about paths, giving terms, and writing out kind of tailored chain rules for tailored to your particular variable situation, and that's all kind of a convenient point of view and everything. But the only reason we know it works is because it comes out of the matrix form of the chain rule, which came from compositions. Right? So anytime you want to write down a chain rule, you're really gonna connect it to it. It's got to come from a diagram that represents a composition. Now, why am I being upset about this? Not all diagrams are. So this one is. That's a composition. You can see the functions pretty clearly, no problem. So that is my first function, f. And here's my second function, g, and you can see the variables that come out of the first one are what go into the second one. That's y1 and y2. No problem. That's following the letter of the law, right? Exactly how compositions work. What if I had some cause, whatever that might be, to write a diagram like this? Can I write down a chain rule for that? And things get scary. Things get weird. This does not represent a composition of functions. Now, by the way, let me persuade you that this kind of diagram can come up. In fact, it's going to come up explicitly. Oh, and I need to hit the... Oh, gosh, what did I do? There we go. It comes up explicitly from looking at these equations right here. And you can see y1 is given to be a function of x1 and x2, so we write that. And then y2 is also a function of x1 and x2. And then you can see the troublemaking one is this one right here. Z1 seems to be a function of x1 and y1 and y2, kind of like that. Okay, fine. So what's the problem? What's the issue? Why don't we just sort of proceed on this? And the reason why is, let's ask the question, what would this partial derivative mean? If I wanted to ask us, what is the partial of z1 with respect to x1? Okay, well, there's z1. Partial with respect to x1, I guess, says I'm going to leave x1 to be the variable. That means I need my other input variables to be constant. And I claim this is already obvious nonsense. And what do you mean I'm supposed to vary x1, but then y1 and y2 aren't allowed to change? Right? Doesn't make any sense. Everybody okay with that? So it's not clear what's going on here. We cannot apply a chain rule to this as we have things set up. Okay, so let me show you how to fix it. It's an easy fix. Certainly in this case, and I don't want to generalize this, but what I'm going to do is I'm going to pretend that I have another variable right there. I'm going to call that, it's going to be kind of a mirror of x1. It's not x1, it's a different variable. It's going to be called x1 star. I'm going to call it x1 star. But because I set up that as technically a different variable, it's got all the same values, right? But it's technically a different variable. Well, then now I have a composition where there's the first function, and there's the second function, and as required, what comes out of the first is what goes into the second. All good, no problem. Composition. Chain rule's fine, we're in business. Does that make sense to everybody? Okay, now, is this legal? Are you allowed to do that? Can I just make stuff up? Well, okay, that's a concern, right? You'll notice that now this Z1, let's see, let me make a better color choice. Z1, I now have as a function of x1 star y1 and y2. Is that the same equation? Well, just keep in mind, x1 star is x1. So from a values point of view, what values of z1 will come out of this? Yeah, exactly the same. Yeah, it's x1 star is all the same stuff as x1. So it's not really going to change anything. But because I've introduced this new, equivalent, but still new variable, now I'm not breaking any rules. Now I'm dealing with an actual composition, and I can use my chain rule. So, handy. Let's see here. We want to compute this partial, the one that we couldn't make any sense out of previously. Right? How are we going to compute that? Okay, well, let's see here. There's Z1, there's X1, and I see three paths. There's an X1 star path, and so there's an X1 star term. And there's a Y1, color choices. There's a Y1 path that gives me the Y1 term, and then there is a Y2 path that gives me a Y2 term. Nothing to it. Good old-fashioned chain rule. Everybody on board? Now, conveniently, you see here I do have this partial of x1 star with respect to x1. What is that? Well, don't forget that x1 star is x1, so this is the world's easiest partial. That's just 1. A factor of 1 just disappears. And there's your chain rule for this situation. Everybody happy? Okay. All right, tricky little move. Yeah.
How would this come up in a question?
Yeah. Well, yeah. This is literally the question that I addressed. So you have a bunch of variables related by a bunch of equations, and then somebody asks you to compute the partial of z1 with respect to x1. Yeah, and so again, if you're not aware of this trick, then you'll take that algebra and you'll produce this diagram, and then if you're honest, you'll say, that's not a composition. We don't know how to do this, right? But then you fix it by introducing the x1 star, and then you just follow the rules, and it's all good. Yeah.
So do you recommend drawing that diagram?
Oh my gosh, yes. Yeah. Oh, I live with, I can't do it without these diagrams. It keeps track of what's where and playing what role with respect to what function, and it demonstrates right there, okay, where are your intermediate variables, and therefore what kind of terms you have, right? So students that, now, I hope this won't be any of y'all, right? But just so you know, what I do see on exams sometimes is that students will see a question like this, not have a diagram. I guess they're doing it in their head or something, I don't know. But they won't have a guide telling them how to keep track of stuff, and they'll have, like an x1 term and a y1 term and a y2 term, and then z2 term. They'll have partial of z1 with respect to z2 times partial of z2 with respect to x1, and I'm like, what? Where did that come? That's not even an intermediate variable. They're writing down extra terms that don't make any sense. Right, so please, yes, absolutely, always have your diagram, and the diagram tells you how to manufacture your chain rule. Right. Okay, question, yeah.
Are you going to have a case where x2 depends on x1 here?
That would be, I would have to, in order to fix that, I would have to sort of prepend yet another function. I would have to have a composition of 3 functions to make that into a legal diagram. So yeah, you can make that work, but it's a kind of ugly that I don't want to say I won't do, but it's certainly not something. No promises, but that would be harder. Yeah. Yes.
Does the order of the partials matter for this, like?
No. I mean, so these are scalar partial derivatives. So if you wanna write these the other way, that's totally fine. And if you want to reorder the terms, you can. For whatever it's worth, it makes sense. If you want a happy grader, right, which I think we all want, then it makes sense to have the terms consistent with at least how you've ordered the intermediate variables in your diagram. Yeah. Okay. All right, so let's talk about how to do second derivatives. Now, just a context thing, this is not in the book. I think that's an oversight. I think it's unfortunate. In my ancient history days as a second major in physics, I did a ton of this stuff. And y'all are engineers mostly, so you won't have exactly the same amount of physics to do that I did. But you're going to have plenty of physics, and this kind of thing can absolutely come up. It's not rare. It's quite common. And I'm going to show you a really important example on the next page. Okay, so ultimately, the big trick is this, but it's not clear why this is a big trick just yet, so I'm going to put a pin in that. We'll come back to it, and we're just going to dive into an example. So z is given as some function of x and y. Let's build our diagram. That's what we got. And then r and theta are polar coordinates. Now, think back to polar coordinates. How do polar coordinates work? X and y are r cosine theta, r sine theta. X and y are functions of r and theta. Let's put that on our diagram too. Okay, so when you have a function that naturally presents as being in terms of rectangular coordinates, but if you want to reconceive of it as being a function in polar coordinates, you are composing a couple of functions. And so now with that in mind, with the understanding that I can view z as being a function of r and theta by way of this composition, let's ask what is that second partial with respect to r. Okay, no big deal. So it seems. Oh, if I can get my eraser to. Oh no, it's died. Okay, let me plug in my thing. Let me pull out my temporary. Hopefully this will work. Okay, all right. Okay, so let's see here. First, we got to take the regular partial of z with respect to r. there's z, there's r, x path, x term, y path, y term. Nothing to it, no big deal. Now, by the way, there's a lot of little micro details in this calculation. I am going to go quickly through the micro details. If you have a question about one of the micro details, I encourage you to just make a little note and then come back to it later, because these are all things that you can kind of fill in the blanks for as needed after. Okay, but having written down this chain rule straight out of the diagram, let me remind you we have an alternative notation for partial of z with respect to x. That's just notation. We haven't used this notation much yet. We're going to use it a lot in this example and the following. But anyway, it's just notation, and likewise, that's just notation as well. The other observation I'll make is that, let's see here, that's an easy partial derivative to compute, and so is that. Because, in fact, we know x and y as functions of r and theta. Right? They're formulas. R cosine theta, R sine theta. You can compute those partials explicitly. Okay, so we have computed now the first partial with respect to r. And now we need to compute the r partial of that r partial to get the second partial that we're actually interested in. Yeah? Everybody with me? Everybody see? There's a lot of, don't get ahead of me, right? But there's a lot to come, but that's where we're at right now. Okay. Let me, for the moment, I want to scratch this off. I'll reveal this stuff later. Okay. All right. Now let's try to make sense out of this expression right here. What are we going to do with that? We are eventually going to be able to make sense out of this from the diagram. So let's see here. First observation, and this is a subtlety. This is something you all have to keep track of. So you're going to be noticing I'm going to be making heavy use of the diagrams. I encourage you all also to make heavy use of the diagrams. Very important. And it says here, we're taking a partial with respect to r. Okay, so I refer back to the diagram. I'm taking a partial with respect to r. And don't forget what that means. Partial derivative means the other variables in its little world are constant. So theta is a constant. That's implicit in the fact that we're doing an r partial, right? So theta is a constant. I get to treat theta as a constant. And by the way, that means that cosine theta and sine theta are constants, right? And multiplicative constants just factor right out when you're doing derivatives. Everybody okay with that? Okay. Now let me show you what would have happened had there been something uglier in their place. So if I had been looking at a r partial of, this is not a constant, and maybe there were something else in here, not a constant. If this had had some r's in it, or if this had had some z's in it, or something, I don't know, whatever. Well, then I'd be looking at a derivative of a product, and I'd have to write down the product rule. But y'all know the product rule. It's just a matter of just writing that out. So anyway, be prepared for the possibility. By the way, there's a homework exercise that's going to be very similar to this, where you will have a product rule that's going to come up. So anyway, this is where you would use the product rule. Okay, so we're down to this, the hard part of which is this. And now I want to take a pause. We're right on the precipice of a landmine. I think I mixed my metaphors there. We're about to step on a landmine right here. And I want to show you what the mistake is first before I show you the right way to think about it. Here's what a lot of students will do. Very common mistake. A lot of students will take this and say, oh, okay, well, I'm taking z And apparently I'm supposed to take a derivative with respect to x, and then apparently I'm supposed to take a derivative with respect to r. So why don't I just call that zxr? And I claim you can't do that. That's a bunch of garbage. That's nonsense. Doesn't make any sense. Meaningless, silly, nothing. Here's why. This seems to be suggesting that z is a function of a bunch of variables that apparently include both x and r. It seems to be suggesting that z is a function of all four of those variables. And that doesn't make any sense. Well, this is not a function. Now, if I were to view z as being just the output from the second function, then yeah, sure, z is a function of x and y. And if I were to view z as being the output from the composition, okay, well then z is a function of r and theta. But you got to pick one, right? Are we talking about z as being the output from the second function, or is z the output of the composition? Those are your choices. And if I were to just try to dream up and just say, yeah, z is a function of all four of these, what, pray tell, would it mean then if I wanted to take a derivative of z with respect to r? For example, what would that mean? That would seem to suggest that we're going to hold all the remaining variables constant, and this is impossible. You can't vary r and have x and y stay constant. You just can't do that. Because x and y depend on r. You change r, you're going to change x and y. This doesn't make any sense. This is garbage nonsense. Everybody see how that's garbage nonsense? Okay, so I want you all to see where the landmines are. Don't step on this landmine. Right? This will blow up your exam question or your homework exercise or whatever. So please don't do that. Yeah. Mm-hmm.
So what would be the correct way?
Yeah. That's my next thing. Yeah. Totally. Yeah, absolutely. So let's talk about what is the proper treatment of this. Let's get rid of that garbage. Proper treatment of this is what I skipped over at the very beginning, and that is to recall that, look, if z is a function of x and y, which it is, when I represent z being a function of x and y by indicating it thusly on the diagram, then so are zx and zy. They are also functions of x and y. And so that's what I do here on this diagram. I'm going to explicitly denote zx as being a function of x and y. So that's where zx goes on the diagram. It is literally a function of x and y. I'm going to indicate it as a function of x and y, and now I know what to do with zx. There it is. And then likewise for zy is on the diagram now explicitly as a function of x and y. So back to where we were, and now we're going to kind of abandon that diagram because we have an improvement of it. You want to compute the partial of, bad color choice. You want to compute a partial of zx with respect to r. All right, well, there's zx, there's r. I've got two paths. Thank you, diagram. Got the x path, which gives me an x term. I've got the y path, which gives me a y term. And altogether, then, that partial is computed by that chain rule. There's really nothing mysterious about it, right? Zx is there. R is there. Two paths, part of a composition of functions, two terms. Yeah.
So we're going like right to left with the chain rule?
Left to right. Well, yeah. So the arrows go left to right. I mean, we pronounce it backwards. We say partial of zx with respect to r. But if you want to say the r partial of zx, then that's recognizing
like
how it's
the piece in green.
Yeah.
Is written.
That's
like,
this green term here corresponds to this green path through the intermediate variable x.
Does the order matter for
as to whether.
No, like, could it
Oh,
be written-
no, these are scalars. You can write them in whatever order you want.
Oh, okay.
Yeah,
So it doesn't matter.
Yeah. If you want to write this as partial of x with respect to r times partial of zx
Yeah.
with respect to x.
That's the same thing.
Yeah, you can. I think what I like about this is that when you pronounce this, then you see the partial x's. You hear the partial x's right next to each other. And I find that somehow more satisfying. Yeah, you say partial of that with respect to that and that. I don't know. I just verbally, it makes the x's more next to each other. It doesn't matter if for whatever reason you like to. That's all good. Yeah. Okay. Is everybody happy with this treatment? Yes.
Sorry, one more thing.
Okay.
The cosine part is coming from this.
Yeah.
Circle cosine? Or-
Yeah. Well, this is polar, but So keep in mind, this cosine theta became this, and then that was the next thing I was going to have to point out. Don't forget to right. Okay, so this is the deep water right here. This is the hard part. This is the thing that makes this work really well. This is the trick, you might say. And everything else is kind of details. Now we do have one other instance of this trick, so let's think that through. We in fact also have to make sense out of the partial of zy with respect to r. So there are those. And let's see here. Well, we get an x path. That gives me an x term. And there's the y path. That gives me the y term. And so that is computed by that chain rule. And then again, easy to forget, but don't forget to copy down your constant sine theta. Everybody good? Okay, it's all over with the shouting. So let's see here. Yeah, so notational freebie, that is just that. No concerns as to whether that makes sense. Z is immediately a function of x and y. This says x partial, and then take the x partial of that. There is no composition. There is no funny business with what's a function of what. It's just zxx. And then likewise, that, and that, and that. And again, we have some easy partial derivatives to compute. Again, details for you all to think through. Again, don't forget these multiplicative constants. And then you'll notice if you kind of multiply and collect terms, it simplifies a little bit right there. Yes?
Did that notation zx, y, does it matter if it's like x, y, or y, x?
In this case, it does not, because we're given that this function is C2. And remember, we have a theorem that says that if you have a function that's, if you have a function that's C2, then the second order mixed partials are equal. So yeah, in this case, it doesn't matter. I think as a point of order, you'll notice, let's see here, how did I do? Okay, yeah, I arguably should have made a point about that when I wrote this. I probably should have written this one here down as zyx at first. Or at least I should have said, C2, right? Because the fact that this is a C2 function is why I can rewrite this as that. So yeah, quibble on my own work there. Yeah, I don't know if that would rise to the level that I would count off for. Probably not. Yeah, right. Yes.
Is the ZXX, is that the preferred notation?
I don't really care in terms of your final answer, but you will notice that it's really nice to have them in this form here, because then they look like variables. They look more like variables, and it's just kind of, I don't know, I find that it feels better at this stage. And then once you've got it into this form, it would seem weird to switch back to the bulkier notation. So I think I don't know. It's aesthetic. It's an aesthetic judgment call. Yeah. I like it better like this. Yeah. Okay. Example. Why we would care about this. And I think this is a really cool example, but see what y'all think. Let's see how my stylus is doing here. We're back in business. Okay. All right. So, good thing for y'all to know about. There's this thing called the Laplacian operator. So this thing right here is called the Laplacian operator. It's shockingly important. Comes up in a lot of different places. If you want to write down the equations of waves or heat flow or how electrons behave, right? Kind of a big deal, all three of these, right? So this is a lot of the tremendous applications in physics all rely critically on this critter right here called the Laplacian operator. It's a really big deal. So it's going to be a big deal in y'all's futures as well. Okay, so that's the formula for it. And it turns out that you can rewrite the Laplacian, whoops, put this in purple. The Laplacian operator, which we initially write in rectangular coordinates like this, you can rewrite it in spherical coordinates like that, I claim. And there's a ton of algebra that goes into seeing how that works and how I know that that's how you can rewrite it in spherical coordinates. And I'm going to kind of wave my hands at how that's done momentarily. The first thing I'm going to observe is, at a glance, kind of feel like we probably like this one better.
Yeah.
Yeah, right. Seems likely. Okay, so we'll come back to that. We'll decide later, after you've seen these in play, which ones we actually like better. Okay. So let's talk about where it comes from. How do I know that this is equal to that? And ultimately, keep in mind, if you have a function f written in rectangular coordinates, then okay, well, yeah, but rectangular coordinates are functions of spherical coordinates. That's how spherical coordinates works, right? We have explicit formulas for x, y, z in terms of rho, phi, theta. Right? And so we have a composition. And so if you wanted to confirm that this is true, that these two things are equal, we could come in here one bit at a time. For example, I could look at second partial of f with respect to theta. Well, there's f and there's theta, and just like on the previous page, you could compute second partial of f with respect to theta. It's kind of like on the previous page. You get this great big expression, right? And it'd be quite a bit worse than what we did on the previous page because there's more trig in spherical coordinates, and there's more variables. There's just kind of more everything, right? And that would be just this part of that monster. Yes?
Will we be seeing the Laplacian on our exam?
You do not have to memorize this formula. Yeah, absolutely not. I have never.
The same thing.
Yeah. I have never in my life memorized this formula, not even when I was a physics major. Yeah, right, absolutely. Yeah, it's too much. It's too ugly.
Do we need to derive it?
Oh God, no.
Oh.
Yeah, no. That would be. Yeah, I've never done that. Yeah. Not that I couldn't. I could do it. If I really wanted to, right? I'm sure I could, but I'm not gonna.
We're all like sweating.
Yeah. No. So I want y'all to understand how to do the calculation. I don't actually want you to do the calculation. Right? Okay. So yeah, so reminder, if you wanted to compute just this little part over here on the end, you can compute that by, well, here's your diagram, do the second derivative chain rule just like on the previous page, totally doable. Just, slowly and carefully keep in mind what's a function of what, and what are your intermediate variables, and just write it down. And then you can do that for all the rest of the derivatives in here, right? And whatever you get here, don't forget to multiply by that, and then whatever you get here, multiply by that, and then whatever you get there, take the phi partial of that. You can just go through and do this whole monstrosity. And if you do all of that, very hypothetically, you would get this. And I don't know who first did all this work, but they had a lot of time on their hands and played around with it. Okay. All right. Now, so what I hope y'all are getting so far is that this fairly compact expression is equivalent to this much less desirable looking expression. And I hope you're wondering, why is he wasting our time with this that we would never want to do? Okay, all right, so here's an example. We talked about the Laplacian. That's this operator here. Otherwise, this operator here, take your pick. We're going to apply that to some function, and the reason we would do so is because, again, if you want to understand gravitational potential, if you want to understand electric potential, if you want to understand electricity and stuff like that, kind of a big deal. Right? Then electric potentials, for example, they obey Laplace's equation. So, all right, we would have to therefore take any candidate, anything that we think might be possibly an answer, a solution to this equation. For example, this, and by the way, this is one of the solutions. If I want to confirm that that is a solution, well, I'm going to have to take either this form of it in the rectangular form and apply the rectangular Laplacian, or I would have to take the spherical form and apply the spherical Laplacian. So now again, here's our choices, and you get to decide for yourself. Free country. You could either do that, like this, or like this. And I know what you're probably thinking. You're still, okay, still, I'm sticking with the rectangular, right? Probably. I did too. All right. Y'all are going to have to do this calculation at some point. Everybody should do it once in their lives. As I like to joke, I've already done mine. It's your turn, okay? And it's a little tedious, but you can see the tedium coming. We got a quotient rule situation, right? We're going to be taking 6 different derivatives involving the quotient rule and fractional exponents, and it's just annoying. It's not hard. It's just long and tedious. If you're tight and efficient with it, you can probably get it done in a page. If you are not careful with how you write things down, if you like to write big and spread things out, it's easy 2 pages. It's a lot it adds up. Okay, yeah.
So is this almost like distributed? Like, can it be rewritten as like the second order derivative with respect to x of that?
Yeah, that's right. It's going to be the x second partial of this,
okay,
and then plus the y second partial of the, yeah.
Okay.
That's right.
And like the same in the bottom.
Yeah. That's right. Okay, so this first, the rectangular expression here, bummer. Right? And you don't want to have to do bummers if you don't have to, and this is a bummer. Okay, this one here, scary, looks like a monster. Oh my God, is he seriously going to make us do this? We are seriously going to do this right now in our heads. We're not even going to write anything down. This one's easy. Swear to God, super easy, and you're going to catch on quickly here. Let's do it. Let's actually start writing terms down, and we'll start by looking at this term here on the end. The very first part of which apparently I'm going to need to compute the theta partial of this expression. How am I going to compute the theta partial of this expression? Oh, there's no thetas in there. That's 0. Haha. Gone. Poof. 0. Right? Okay, so all that is 0. So, sweet. Okay, let's do it again. Let's look at this term. Ooh, wow, that could get weird. Except, I'm running out of colors. The very first thing I need to do is take a phi partial of this expression that has no phi's in it. 0. Poof, gone. Nothing. Bam. All of a sudden, this spherical Laplacian's not looking that bad. Right? That's pretty sweet. All right, now we're going to have to do just a teeny tiny, itty bitty little bit of work on this last one. It's not that bad. But I am going to have to take the rho partial. This does have a rho in it. Okay, now I think, all right, fine. The rho partial of constant over rho, it's going to be like there's a minus sign or something. Some constant over rho squared. Right? Okay. Constant over rho squared times rho squared gives me constant. So this thing right here is a great big constant, and very conveniently, whatever kind of a derivative you're taking of a constant, 0. And so that disappears also. And we're done. And I didn't have to write down all the algebra that we needed to do to compute this spherical Laplacian applied to this electric potential candidate. We were able to do in our heads and confirm that, yes, this is 0 as required, and so done. So that is a pretty cool lesson. Do not sleep on spherical coordinates. They are awesome in a lot of cases, right? This is super much better than that, right? And this is not the only such situation. We're going to see some cool examples in when we get to integrals, when we get to multivariable integrals, which is actually pretty soon. Maybe next week, I forget exactly. Spherical coordinates, well, that'll take us an extra week or two. Anyway, so not that far into the future, spherical integrals can be really, really powerful as well. Much nicer. Yeah. So,
would this be part of our exam on Friday?
This is all fair game for the exam on Friday, yeah.
Well, we wouldn't have to memorize it.
No.
So we would be given it or something.
Yeah, this is no. I've never memorized this in my life, and I'm not going to make y'all memorize stuff I haven't memorized. Yeah. It's in a book. This has come up on when I was a undergrad doing a lot of physics, right? I had that page of my textbook dog-eared, and I was using this all the time, but I didn't memorize it. Yeah.
So what context would we would just have to?
Right. Okay. So the reason that I'm showing you this is because I wanted to persuade you that spherical Laplacians are awesome, and the reason that matters is because spherical Laplacians come out of second derivative chain rule, and so basically the methods that we did in this example right here, all the examples, all the work that we did in this example on this page, this is the roadmap for how you demonstrate that the fun stuff we did on the next page actually works.
Okay, so Laplacian is just like one example of the second order.
The Laplacian. It's just an example of why being able to deal correctly with second partials in the context of the chain rule is important. It's because this kind of stuff comes up. And again, notice nothing obscure about these examples. You want to understand how heat moves? That's not a niche problem, right? That's a big deal. That's everywhere, right? Okay, I saw a hand back there. Yeah.
I was just asking, is the chain rule the end of the exam material?
Is it the what now?
The end of the exam material.
Yeah, I think it sort of has to be because we've got we're kind of out of time. So we did finish 2.5. We did finish 2. So 2.5 is fair game. And that'll be the last entry I'll be making on the calendar. Yeah. Okay, so we're out of time. We're drawing the line right here. See y'all on Wednesday. Have a good one. Okay, let me get the recording stopped here.